Nowadays, the trend of using climbing robots to replace human labor in high-risk and high-rise tasks has been gaining momentum, leading to a surge in demand for high-performance climbing robots. This trend has motivated our team to develop a climbing robot that can climb both faster and nimbler. We observed that geckos, among the planet's best wall climbers, intentionally control their spine oscillation to extend their reach. Given this observation, we hypothesized that the incorporation of an active, flexible spine in the gecko-inspired climbing robots will increase its climbing speed compared to models equipped with only a rigid spine.
To test our hypotheses, we developed the climbing robot's design by breaking it down to three main subsystems. Firstly, the active spine system, driven by a closed-loop controlled stepper motor, emulates the flexible movement of a gecko's spine. Secondly, the vacuum pump adhesion system comprises two vacuum pumps, two relief valves, and four suction cups. To maximize efficiency, synchronized diagonal leg pairs will share the same pump and valve. Thirdly, the leg motion mechanism is constructed from carbon fiber plates and 3D printed brackets for optimal strength to weight ratio. This system incorporates 8 servos, including 1 minute servo per leg for lifting and dropping, and 1 standard servo for translation movement. All actuators across the subsystems are powered by 12 volts or 6 volts power supplies and controlled by an Arduino Mega.
In our robot design, we had an emphasis on spine curvature, compactness, and weight reduction. To analyze the effect of an active spine in our Gecko robot, we considered two different spine designs. Design 1 uses a stepper motor centrally located within the spine. A set of spur gears connected to the motor shaft transmits power to two adjacent shafts attached to the head and tail of the robot. This setup was easier to design and assemble within the compact frame of our robot. We were also interested in whether a more natural spine curvature would affect our results. While Design 1 helps us in our research, it features a less natural curve because the tail and head rotate about the endpoints of a central rivet spine. Conversely, Design 2 features a multi-segmented spine with 3 to 4 joints to create a more natural curve. In Design 2, we place the motor on the tail. The tail is formed by a succession of segments attached with shafts and side-mounted springs. Wire attached to the motor pulley is threaded through the springs and holes on each segment and fixed to the final segment on the head. When actuated, the pulley pulls the spine in either direction. The design is inspired by continuum robotics. We created simulations of the leg and spine motion to help make sure that our motion control would be what we expected and made full CAD renderings to ensure it fit within our size constraints. Despite experimenting with two designs, we used Design 1 as our baselines for our test.
With the full robot settled up and the gauge cycle program, we tested its climbing speed on flat surface with spine off and spine on. This test proves our hypothesis, and our active spine design increased its climbing speed 21%. We also tested its ability to adhere on vertical surface. We then started to gradually increase the surface angle, and our final goal is make it climb on vertical surface. However, we noticed some issue when the angle reaches 25 degrees. One pair of the leg can't robustly stick to the ground and starts to slip when climbing. We then found this is because one of the pump is too weak to provide sufficient force on the feet and causing such slippery. The other pair of leg has excellent performance. The power consumption for rigid and active spine is also worth to mention. In general, the active spine consumes 60% more power than rigid, but this could be reduced by optimizing the spine design or add more lubrication to the segments. In conclusion, integrating an active spine mechanism into a climbing robot has proven to significantly enhance its operational performance. Moving forward, these findings will guide the refinement of our model and encourage further research into bio-inspired robotics, aiming to optimize and adapt this mechanism for broader, real-world applications.